Hello class, today we're going to look at section 1.1 and we're going to start off by looking at the number system. So let's go ahead and scroll down. Throughout the lesson, if I'm talking too fast or moving too fast, feel free to pause so you can catch up. So what we're dealing with in our number system are the types of numbers that we're going to work with. We're going to start with the inside smallest box that we have here, the natural numbers. The natural numbers are also known as your counting numbers, and the reason that they're called that is these are the numbers you would use if you were going to count. So if you started counting, you would start at 1 and work your way out to 3, 4, and it would go all the way to positive infinity. This would be considered our natural numbers or counting numbers. The next box out, notice that it's a little bigger, so it has a little more. It's going to include all the numbers we just talked about, the 1, 2, 3, 4, and so on. But it's also going to include your whole number, and our whole number is the number with a hole in it, which is 0. So the only difference between natural numbers and whole numbers is the number 0. Our next box out, getting a little bigger. Again, we're going to include everything below it. So we have the 0, we have 1, we have 2, we have 3, 4, and so on. Integers now is going to work to the left, or it's going to work in the negative direction. So I'm going to have -1, -2, -3, and this is going to continue left forever. Now these first three types are not going to have a fraction and are not going to have decimals. The fractions and decimals are going to start when we get to rational numbers. So we're going to work left and right forever. So we have all the numbers we just talked about, plus we're going to start to have fractions and decimals. Okay. So now we have fractions and decimals. And these are decimals that either end or they repeat. Okay, so rational numbers are integers, whole numbers, natural numbers. But we also have fractions, and we have decimals that end or repeat. Off on to the right over here, we have our irrational numbers. Now, irrational numbers, notice that they sit by themselves over here. They're not included in any of these other boxes. So none of these numbers that we've talked about so far are considered irrational numbers. So irrational numbers are decimals that never end and never repeat. A number that is an example would be pi. That's a decimal that goes on forever. It doesn't repeat. Another example would be a square root. So if we have the square root of 2, that is a decimal that doesn't end or doesn't repeat. Now if we had something like the square root of 4, well, the square root of 4 simplifies to give us 2, so that would be actually considered a natural number, whole number, integer, and rational number. So we're talking about square roots that don't simplify as an example of an irrational number. Now if we look at all of these combined, that gives us the real number system. Okay, so as we go through this course, we're going to use different types of numbers depending on the application that we're working with. Okay, let's continue on with section 1.1 and look at set notation. So this is a way to write out a set of numbers. So we have the set of is represented by our notation on the outside. All elements of x, so we may end up seeing a different variable like y or z here. The bar is read as such that, and then the back portion of it, this will be what we're actually talking about for our set of numbers. So x has a given property p. So this may say something like x is greater than 5. So this will represent what we're looking at. So let's look at our first example. We want to write each set by listing its elements. So we want to actually write out what numbers this is talking about. So we read this as z, such that z is an integer less than or equal to 4. So some keywords we want to pick up on is integer, and we have less than or equal to 4. So let's go ahead and look at what numbers we're talking about. Less than or equal to 4 means we can start at 4 and we're working less than. Now, an integer tells us that we're not going to have any fractions or decimals, so the next number less than or equal to 4 is 3, and then 2, and then 1, 0. Since it's an integer, we keep going in the negative direction. Now this is going to go on forever, so to represent that, we write the 3 dots, and then we fill in our parentheses on the outside. So this is the set by listing its elements. We want to actually list the numbers that are less than or equal to 4. Next example we have x such that x is an irrational number that is also rational. Well, if we go back to the boxes we were working with, we remember that irrational numbers sat on its own over here, and rational numbers were included at this box. Notice how there's no overlapping of the two. So when we're working with trying to find a number that's irrational and also rational, this isn't going to exist. So we have the empty set. That represents that there isn't a number that falls into this category. Okay, so now we're going to work in the opposite direction. We're going to try to get the set notation from the list of elements. So we want to go ahead and end up with a result that looks like this top portion here. We have the set braces, we have x such that x has the property, and this back part is where we're going to talk about what we have. So let's go ahead and look at our first one. So we can get our set braces set up. We have x such that x. Now we want to go ahead and talk about the numbers we have. So we have the numbers 2, 4, 6, and 8. These are all even numbers, and these are all numbers less than 8. Now we want it to stop at 2, so it shouldn't keep going. So we want to use the number type that doesn't go into the negative direction. And our number doesn't go to 0, so this is dealing with natural numbers. So x is an even natural number less than or equal to 8. Always close our set braces. So we have less than or equal to 8. It's even numbers, and we're natural numbers because we're only going to 2. See if you can come up with the description for our second example. I'll help you get started. X such that x, and then go ahead and describe the 4, 8, 12, and 16. Alright, if that wasn't long enough, go ahead and pause and keep working on it, and then unpause when you're ready to go. So notice that we go 4, 8, 12, 16. So these are multiples of 4, and they're greater than 0. And the 3 dots tell us that this goes on forever. So x is a multiple of 4 greater than 0. So we have x is a multiple of 4 greater than 0. So we should be able to work back and forth between the two notations. Let's go ahead and continue on. And we're going to look at a number line. So now we're going to take these numbers that we've been talking about and we're going to locate them on a number line. So let's look at our list of numbers and put them onto our number line. Let's start by looking at 0. 0 is a popular one that we want to put on our number line. We could put it in the center. That would be a good spot to do it. Then we know the right side is going to be all of our positive numbers. Left side is going to be all of our negative numbers. And I'm going to cross off 0 since we used it. Now if we just make a mark of -1, -2, and so on, what we're going to end up finding is that we need to find out where -1/4 is. I know it's between 0 and -1. If we turn this into a decimal, that may help. That would be -0.25. Maybe that's a little useful for you. So we go ahead and see, well, it's a quarter now. A quarter makes sense, so I'm going to go just a quarter of the way, and we have -1/4. Now, 6 over 5. Well, if I take 5 and divide it into 6, that's going to go in once, and I'm going to have 1/5 left over. So we can see that it's more than -1. And it's going to be 1/5 more. So if we have -2, we only have 1/5 more, which is just going to be a little bit further. And that gives us -6/5. Again, you can go ahead and divide these to get your decimal if that helps you. Okay, so we've used these two. Now in the opposite direction, we have a 1. If we look at our first value, 5 divided by 6, that doesn't go in once, so it's less than 1. So we can go ahead and identify. If you wanted to, you could break this up into 6 spots and then count 5 of them out, and that would tell you where 5, 6 is. So I'm going to put it pretty close to 1. It's a little further. 13 divided by 4. Well, 4 goes into 13. So we have 3 times with 3/4 left over. There's 1. There's 2. There's 3. And there's 4. So we have 3. So 1, 2, 3, and then another 3/4. So that would be 13 over 4. Five 5.2. Well, there's 5. Here's 6. So again, we're just past 5. That would leave us at 5.2. 2 goes into 11. 5 and leaves us with 1/2. Now we want to check and see, well, 5.2 and 5.5. Well, 1/2 is 0.5, so this is equivalent to 5.5. So that tells us that it's a little further past. We have 5.5. We're taking the numbers and putting them onto a number line. What may be helpful for you if you have some issues with these, some of the fractions, is use that calculator, turn them into decimals, and see if that helps you find where those values are. The next concept we're going to look at is absolute value. So when we're looking at the absolute value, this is the distance on a number line from 0. So if we look at our value here, and we're talking about -5 and +5, the absolute value of +5, the absolute value of -5 is both a distance of 5. So that's why both of these are equal to 5. So absolute value is talking about the distance from 0 to whatever we're working with. In this case, it was 5 and -5. So let's look at a couple of these where we're just simplifying. So we're asked to find the absolute value of -19. Again, if I'm moving too quick, go ahead and pause me and then catch up. Or feel free to rewind me. Absolute value of 19. Again, we're trying to figure out how far is -19 from 0. Well, it's 19 units. We're not worried about the direction right now. We're just worried about how far it is. So the absolute value of -19 is 19. Absolute value of a fraction, 3/4. Again, we're still trying to figure out how far it is from 0. So the absolute value of 3/4 is it's 3/4. Now we're dealing with a few operations where we're going to work our way through. So let's start with the absolute value of -9. Well, the absolute value of -9 is 9. I have a minus sign between the two. Absolute value of -3 is +3, but I'm subtracting it. 9 minus 3 is going to give me 6. So notice how I went through the steps of finding the absolute value of each and then taking the subtraction. Let's look at the other one. Go ahead and pause me if you want, give that one a try, and then unpause me and see if it works. So, welcome back, if you pause me. And we have the absolute value of -1. It becomes a +1. This time we have a plus between the two. Absolute value of -2, +2. We have a subtraction. Absolute value of -3 is +3. So notice that the plus and the minus in between the absolute values doesn't change. We're just talking about the value on the inside. Well, 1 plus 2 gives me 3, and I still have a -3. 3 minus 3 gives me 0. So the absolute value finds the distance from 0. Okay, we're going to look at an application problem where we're using negative numbers to represent the depth of some coral. So we have a few different sites where we have the depths listed, and we're going to answer some questions about them. So it says, what site is the deepest? So this value is the distance from the top of the water. So this is how far down they're going. So the deepest would be the largest negative number, which would be site F. So we have it's negative 16,470 feet below the surface. The second one is, what site is the shallowest? So the shallowest is going to be the one that is not the deepest. And we're looking for negative 6,669 feet below the surface. So that was site E. So just using your negative numbers to represent the depth. Again, pause me if I'm moving too fast. so we're going to look at equations and inequalities. I know this section sort of jumps around. So the following statement is an equation. 5 plus 3 equals 8. Notice the equal sign. So an equation is a statement that two quantities are equal. So we have the 5 plus 3 is equal to 8. This makes an equation. And we'll start to work with some equations where we have variables x plus 3 equals 8, and we're going to have to solve that. That's our equation. Scroll down a little bit. We have an inequality. So the following is an inequality. 2 plus 4 is not equal to 8. Okay? Inequality means that it's not equal to it. So it's a statement where two quantities are not equal. I know when we think of inequalities, we think of the less than or equal to, greater than, greater than or equal to, but you also want to think of the not equal to sign. That's part of your inequality. Let's look at a few of those other inequality symbols. So reading from left to right, the symbol means is less than. So we could have x is less than 5. Or maybe actually use some numbers. 0 is less than 4. So you want to read from left to right, and this represents our less than. We also have reading from left and right. This symbol means is greater than. So I could have x is greater than 2. This would be all the x numbers greater than 2. Or maybe we have 5 is greater than 1. So you want to read from left to right. So just looking at our equations and inequalities a little bit. Now let's look at some examples from the book where we're taking a statement and we want to turn it into an inequality symbol. So we want to look at this not equal to. So that is our symbol that we had on the previous page. So now all we want to do is we want to plug in the 0 and we want to plug in the 5x plus 3. So 5x plus 3 is not equal to 0. Another example of working with these. Go ahead and pause me and see if you can figure this one out. This one's a little tricky. Okay, welcome back if you paused me. So this one's saying 3x is between -3 and 4. So let's write that out first. So we have our 3x. It's between -3 and 4. So now we have the second part of it. So this is the part that we've identified so far. Let's use a different color. Now including -3. So including -3 means we want to be able to use -3 as a value. So what that's telling you is this is going to be one of the equal to signs. And we want it between, so we want -3 to be less than or equal to 3x. So we want 3x to be in the middle or between these two. So that means that -3 is the left point of our values. So that means that -3 is less than or equal to 3x. Now for the 4, we want the excluding 4. So that means that 4 is not an answer, but we want everything just to the left of it. So to represent that, we just use a less than symbol. So this is saying 3x is less than 4. It can't be 4, but it can be everything just below it. That's the difference between using the equal to underneath and not. Okay, the next thing we're going to look at is interval notation. So we're taking our set and write it into interval notation, then we're going to graph the interval. So let's talk a little bit about interval notation. Interval notation uses brackets and parentheses. So to determine which one to use, the less than or the greater than symbol tells us to use a parenthesis. The less than or equal to or the greater than or equal to will tell us to use brackets. This probably make a little more sense once we actually try an example. So let's look at our first example. Set notation. So we have the problem x such that x is greater than -1. Okay. So x is greater than -1. So that means I'm going from -1 greater than. Oh, and if I'm going greater than, I'm going all the way to infinity. It doesn't give me a stopping point. Now, the greater than symbol tells me that I should be using a parenthesis. So notice that the greater than is telling me to use parentheses. So I'm going to have a parenthesis on the -1. Now when we're working with infinity or negative infinity, we want to use a parenthesis always on the infinity symbols. This isn't a number that we can actually include, so we want to use that parenthesis. Next part is to take this information and put it onto a number line. So we have 0, we have -1. Now we're going to use our interval notation to help us put this onto a number line. The reason and the way it helps us is if you look at the parentheses here, that is the same parentheses that I'm going to use at -1 on the number line. To represent the rest of this, to represent that we're going greater than, we want to just draw a line on here representing that it's going right forever. Okay, so your interval notation will tell you to use a parenthesis or bracket. So if we had used a bracket on our interval notation, we'd be using a bracket on our number line. Alright, let's try another example of this. You can go ahead and pause me if you'd like so that you can try the problem on your own and then come back and check your answer. Welcome back if you actually paused me. If you didn't pause me, let's go ahead and go through the problem. So this time we're dealing with our x value is between two numbers. So what we're going to do is we want to use those two numbers that we have. Make sure we have 0 to 3. Now to determine the brackets and the parentheses, we look at the symbols. The less than again tells me that I should have a parenthesis. The less than or equal to on the 3 tells me I should use a bracket. Okay, so this represents all the numbers from 0 to 3. So 0 is less than x, which is less than or equal to 3. And the last part is to go ahead and put this on a number line. So we have 0. We have 3. And again, just like we used a parentheses here, we're going to use a parentheses on 0. And we're going to use a bracket on 3. And these are going to be our solutions in between here. So once you get the interval notation set up, that should give you an idea of what the graph is going to look like. Okay, so that was 1.1. Again, you're welcome to rewind, do whatever you need to do to go back, see some other examples. That should give you a good start to your homework. Hope it was helpful.